Allow your mind to drift away from the day's concerns. Imagine yourself floating in a vast, quiet, and weightless space. The only light comes from the gentle and wavering glow of distant suns. Each star is a distant sun with its own family of worlds. We are about to embark on a journey to the farthest reaches of our cosmic neighborhood. We will explore the mysterious visitors from beyond our solar system. Let the mystery of the cosmos lull you into a state of deep relaxation. As you listen to the story of these interstellar wanderers, feel your body growing heavier and more relaxed. Breathe in the stillness of the universe, and breathe out any lingering tension. Your journey into the stars and into restful sleep begins now. Humanity has gazed at the stars for millennia, wondering if we are alone. For centuries, our understanding of the cosmos was limited to our own solar system. We studied planets, asteroids, and comets, all bound by the sun's gravity. Theoretical astronomers long predicted that objects from other star systems could pass through. These interstellar travelers would be moving too fast to be captured by our sun. They would follow open-ended hyperbolic trajectories unlike the closed ellipses of local objects. Finding such a visitor was like searching for a single unique grain of sand on a vast beach. The first confirmed discovery would revolutionize our place in the cosmos. It would prove that our solar system is not an isolated island, that pieces of other worlds would come to us. That moment finally arrived in the autumn of 2017. A telescope in Hawaii designed to watch for asteroids made a historic detection. It spotted a faint point of light moving against the backdrop of fixed stars. Its motion was immediately strange and calculated to be extreme. The Pan-STARRS Observatory had found our first confirmed interstellar guest. It was given the name UAMUA, Hawaiian word for messenger from afar. This name captured the profound nature of this discovery. UAMUA was a scout from the vast galaxy beyond our own stellar doorstep. Its arrival marked the beginning of a new field of astronomical study. Just 2 years later, in 2019, a second visitor was identified. This object was named Borisov after its Crimean discoverer. Borisov was dramatically different from UAMUA in almost every way. It displayed a clear coma of gas and dust, a classic cometary tale. Its familiarity made it no less significant as a scientific sample. These two objects proved that interstellar visitors are diverse and likely common. Their detection was not a fluke, but a sign of what was always passing by unseen. They offered us our first tangible pieces of other planetary systems. We could now study materials formed around another star. This was comparative planetology on a truly galactic scale. The discoveries of UAN Borisov shattered our cosmic isolation. They opened a new window onto the formation and evolution of entire star systems. How can we be certain that an object is from another star system? The key evidence lies in its orbit and its velocity. Objects born within our solar system all orbit the Sun. Their paths are elliptical, shaped like slightly stretched circles. They are gravitationally bound to our Sun, forever looping around it. An interstellar object follows a fundamentally different path. It moves on a hyperbolic trajectory, an open curve that resembles a shallow arc. Think of it as a cosmic highway that enters the solar system and then leaves forever. It does not complete a full orbit around our Sun. The most telling number is its eccentricity. A perfect circle has an eccentricity of 0. Planets have eccentricities very close to 0. Comets have more elongated elliptical orbits with higher eccentricities. But any object with an eccentricity greater than 1 is on a hyperbolic path. It is moving too fast to be held by the sun's gravity. Oumuamua had an eccentricity of about 12. This number was far beyond any value seen for a local object. It was unequivocal proof of an external origin. Its velocity when far from the sun was another clue. This is known as the hyperbolic excess velocity. Local objects have nearly zero excess velocity relative to the sun. Oumuamua was moving at about 26 kilometers per second. This speed was not imparted by our sun, it was brought from elsewhere. Borisov exhibited similar orbital characteristics confirming its interstellar nature. These precise orbital measurements are the gold standard for identification. They tell us an object is just passing through a temporary guest in our skies. Its journey began around another star in a distant part of the galaxy. It was ejected from its home system by gravitational interactions. It then drifted for millions, perhaps billions of years through interstellar space. By pure chance, its path intersected with our solar system. We were fortunate our telescopes were looking in the right direction. We captured a brief glimpse of a traveler on an epic journey across the galaxy. Discovering these faint, fast-moving objects requires a global effort. It relies on a network of powerful telescopes that constantly scan the heavens. These surveys are designed to map the sky night after night. They look for any point of light that changes position or brightness. Their primary mission is planetary defense, finding asteroids that could threaten Earth. But this same technology is perfectly suited for spotting interstellar interlopers. The Pan-STARRS telescope in Hawaii is a pioneer in this field. Its camera has 1400 megapixels, one of the largest in the world. It can photograph an area of sky 36 times the size of the full moon. It repeats these observations over and over, comparing the images with powerful computers. Software algorithms search for anything that moves between exposures. Most moving objects are known asteroids within our solar system. But on October 19, 2017, Pan-STARRS found something different. The object, later named Oumuamua, was detected as a faint streak of light. Its speed and trajectory were calculated within days, revealing its extraordinary nature. Other observatories around the world immediately joined the hunt. The Very Large Telescope in Chile, the Gemini telescopes, and many others. They pointed their immense mirrors at this visitor to gather more data. This rapid response is crucial because these objects are fleeting. They are moving fast and will soon be too distant and faint to study. The discovery of Borisov followed a similar pattern. It was found by an amateur astronomer, Gennady Borisov, using his own telescope. His remarkable find highlights the role of dedicated sky watchers. Professional observatories then confirmed its interstellar trajectory. This global network acts as a fine mesh net trolling the cosmic ocean. It ensures that even elusive objects like interstellar visitors have a chance of being caught. Without these systematic surveys, we would remain blind to these messengers from the stars. While ground-based telescopes make the initial discoveries, space-based observatories provide unparalleled detail. They operate above the distorting effects of Earth's atmosphere. The atmosphere blurs starlight and blocks certain wavelengths of light. Space telescopes provide crystal clear views and access to the full electromagnetic spectrum. The Hubble Space Telescope played a vital role in studying both Oumuamua and Borisov. For Oumuamua, Hubble was tasked with precise tracking. It helped astronomers refine the object's trajectory with extreme accuracy. This data was essential for confirming its hyperbolic path. It also helped rule out any significant non-gravitational forces affecting Oumuamua. although later analysis would reveal a small but mysterious acceleration. The comet bursts of Hubble provided stunning imagery and spectroscopy data. It captured the comet's structure as it swung around the Sun. Its observations helped determine the composition of the coma. Hubble showed that Borisov was releasing water vapor and cyanide gas. This chemistry was similar to comets from our own Oort cloud. This suggested that planetary formation processes might be universal. The James Webb Space Telescope represents the next giant leap. Its powerful infrared instruments can analyze the chemical makeup of such objects in incredible detail. Infrared light is ideal for studying the heat signatures of molecules. Webb can identify ices and organic compounds on the surface of a small faint body. It could one day study the next interstellar visitor and determine its complete molecular fingerprint. Future space missions are already being planned specifically for interstellar objects. The European Space Agency is developing the Comet Interceptor mission. This spacecraft will wait in a parking orbit far from Earth. It will remain dormant until a suitable pristine comet or interstellar target is found. Then it will be dispatched to rendezvous with the object. This is our best strategy for getting a close-up look at the next MUA. Only by visiting these objects can we truly understand their nature and origin. The more we learned about MUA, the more mysterious it became. Its light curve revealed its first major puzzle: its shape. By measuring how its brightness changed over time, astronomers deduced its rotation. The variations were extreme, suggesting an object with a highly elongated form. MUA was not a roundish blob like most asteroids and comets. It was estimated to be at least 5 to 10 times longer than it was wide. Some models suggested a cigar shape, others a flattened pancake. This was unprecedented in our solar system. Nothing natural we knew of was so elongated. The second and greater mystery was its complete lack of a visible coma. Comets are icy bodies. When they approach the Sun, their ices heat up and sublimate. This releases gas and dust, creating a glowing cloud around the nucleus called a coma. MUA showed no coma, no dust, tail, nothing, despite its close approach to the Sun. It appeared to be a bare rocky or metallic object, a dry asteroid. Yet careful analysis of its trajectory revealed a slight anomaly. It was accelerating away from the Sun just a tiny bit more than gravity alone could explain. This is known as non-gravitational acceleration, and comets exhibit it all the time. The rocket effect of outgassing material pushes the comet slightly. But if MUA was outgassing, why was there no coma or dust to see? This was the central contradiction that fueled intense debate. One theory proposed it was made of molecular hydrogen ice. Hydrogen ice could sublimate without leaving a visible dusty trail. But the conditions to form and preserve such a large chunk of hydrogen ice are incredibly rare. Another theory suggested it was a chunk of nitrogen ice. This could also explain the acceleration as nitrogen sublimated in sunlight. This theory posits it was a fragment from a Pluto-like world in another system. A third and more controversial idea was the light sail hypothesis. It proposed the acceleration was caused by radiation pressure from sunlight. This would require an object of extremely low density and large surface area. A man-made light sail for spacecraft uses this very principle. This led to suggestions that MUA could be artificial debris. The scientific consensus strongly favors a natural explanation. But the exact nature of that natural explanation remains elusive. MUA challenged our categories and forced us to think creatively. It showed us that nature can produce objects far stranger than we had imagined in our own backyard. The puzzling characteristics of UA naturally led to broader speculation. Scientists are explorers of the unknown and must consider all possibilities. The planetary fragment hypothesis is a compelling natural explanation. It suggests MUA was a piece of a planet shattered long ago. When planetary systems are young, gravitational forces are chaotic. Protoplanets can collide or pass too close to giant planets. These events can rip worlds apart, ejecting fragments at high speed. A shard from a rocky planet could explain the lack of ice and outgassing. A piece from a Pluto-like dwarf planet with nitrogen ice fits the acceleration data. This theory turns interstellar objects into forensic evidence. They become clues to catastrophic events that shaped other solar systems. Studying them is like studying meteorites, but from infinitely farther away. The more controversial hypothesis is that of an artificial origin. This is not the preferred explanation, but it is a testable one. The scientific method requires that we can imagine evidence that would disprove an idea. For the artificial hypothesis, such evidence would be the discovery of a vast population of similar objects. If we find many UMUAs, it becomes less likely any one of them is artificial. The focus of this hypothesis is not on purposeful aliens, but on derelict technology. It could be a discarded light cell from an ancient civilization, or a fragment of a spacecraft that suffered a catastrophic failure. The key point is that it would be a piece of technological debris. It would be no more a sign of active aliens than a bottle on a beach is a sign of the person who threw it in. This idea was proposed by astronomers like Lode to encourage rigorous thought. It forces us to ask what evidence would truly convince us of extraterrestrial intelligence. It also highlights the potential for future discoveries to upend our understanding. For now, the vast majority of astronomers find the natural explanations more plausible. But the mystery of UA remains officially unsolved. It serves as a humbling reminder that our knowledge of the cosmos is still incomplete. It is a beacon pointing toward the unknown wonders that still await discovery. The legacy of MUAN Borisov is a renewed passion for interstellar hunting. Astronomers are not content to wait for the next visitor to be discovered by chance. They are building new tools and designing new missions to actively seek them out. The Vera C. Rubin Observatory is the most anticipated of these new tools, scheduled to begin operations in Chile in the coming years. Its mirror is enormous and its camera is the largest ever built. It will scan the entire visible sky every few nights with incredible sensitivity. It is expected to be a game changer for the detection of interstellar objects. Projections suggest it could find one such object every single year. Perhaps even more if our current estimates of their population are too low. This will transform the field from studying rare anomalies to analyzing a population. We will be able to understand their different types, sizes and compositions. We will learn if MUA was a weird outlier or one of a common class. This statistical power is essential for answering the fundamental questions, but finding them is only the first step. We need to study them up close. This requires a spacecraft to intercept them during their brief passage. The European Space Agency's Comet Interceptor mission is a bold step in this direction. It is the first mission designed with an interstellar target in mind. The spacecraft will launch and then wait at the Earth's Sun Lagrange point 2. This is a stable gravitational point in space far from Earth. It will wait there until a suitable target is found, perhaps an interstellar object. Once a target is identified, the spacecraft will fire its engines to rendezvous. It will then fly past the object, taking high-resolution images and measuring its chemistry. This mission could provide the first close-up look at a piece of another solar system. It would answer so many questions about MUA's shape and composition. It would tell us if Borisov is truly a universal type of comet. The data returned would be priceless for understanding planet formation across the galaxy. A flyby mission like Comet Interceptor would be revolutionary. But an even greater dream is to rendezvous with an interstellar object, to match its speed and trajectory and fly alongside it for an extended period. This would allow for detailed mapping and possibly even sample return. The challenge is immense. These objects are moving incredibly fast. MUA was traveling at over 90,000 kilometers per hour relative to the Sun. To catch up to it, a spacecraft would need to achieve a similar hyperbolic velocity. Our current rocket technology makes this extraordinarily difficult. It requires powerful propulsion systems and clever gravity assists. Nuclear thermal propulsion is one technology being studied for such missions. It could provide a much higher specific impulse than chemical rockets. This means more thrust from less fuel, making high-speed chases feasible. Another concept is to use a solar sail propelled by the pressure of sunlight. A large enough sail could theoretically accelerate a probe to tremendous speeds. It could be deployed to intercept an interstellar object detected early. These missions are still in the realm of concept studies and long-term planning. They represent the next frontier in robotic space exploration. Beyond just visiting these objects, there is a visionary idea to use them. They are natural transportation systems moving between stars. A future civilization might learn to hitchhike on these cosmic wanderers. They could place instruments on them, turning them into free interstellar probes. This is the stuff of science fiction for now, but it sparks the imagination. The study of interstellar objects connects our present to a vast future. It reminds us that our solar system is part of a dynamic and interconnected galaxy. We are just beginning to learn how to read the messages carried by these silent travelers. Their stories are written in their trajectories, their shapes, and their chemical signatures. Our task is to build the tools and the knowledge to understand them. As we conclude our journey among the interstellar wanderers, let your mind settle like stardust drifting gently through space. The mysteries of UAN Borisov are safe in the hands of scientists. You can release all thoughts and questions into the quiet of the universe. Picture these silent travelers on their endless paths between the stars. They are peaceful messengers on voyages that span millions of years. There is no urgency here, only the slow steady rhythm of the cosmos. Feel the profound peace that comes from being part of something so vast. With each breath, let your body sink deeper into rest. The infinite darkness of space is a blanket of tranquility. The distant stars are gentle reminders of wonder and beauty. Allow the silence of the void to wash over you, carrying you into a deep and restorative sleep. Good night.